Diffusion and diffusion furnaces in semiconductor industry. Welcome to this presentation on diffusion and diffusion furnaces in the semiconductor industry. Diffusion is a core process in semiconductor fabrication, where dopant atoms are introduced into silicon wafers to alter electrical properties and form critical device structures like source, drain, and base regions. This process depends on atomic diffusion principles, which govern how atoms move through a solid material, influenced by factors such as temperature, concentration gradients, and time. Understanding these fundamentals is essential for process optimization. We'll explore the equipment technology behind diffusion, specifically the design and operation of high-temperature furnaces that enable controlled and uniform diffusion. These furnace systems include components for gas delivery, temperature control, and automation. Finally, we'll connect these concepts to industry applications. Diffusion impacts device performance, yield, and scaling, making it indispensable for modern electronics. Through this journey, we aim to understand the foundation of how electronics are built from the atomic level up. Introduction to semiconductors. Semiconductors are a unique class of materials that have electrical conductivity levels falling between those of conductors and insulators. This intermediate property is what makes them incredibly valuable in electronics. While conductors like copper allow electricity to flow freely, and insulators like rubber resist electrical flow, semiconductors can be precisely controlled, allowing or blocking current as needed. This controllability enables the creation of transistors, diodes, and integrated circuits, which form the backbone of all modern electronics. Among semiconductor materials, silicon stands out as the dominant choice. Silicon is used in approximately 95% of all chips due to its excellent electrical properties, abundance, and ability to form a stable oxide layer. Other materials such as germanium and gallium arsenide also play specialized roles, especially in high-speed or optoelectronic applications. Understanding these materials is the first step to understanding how devices function at their core. Introduction to semiconductors. Semiconductors have two key properties that make them essential for modern technology. First, they are temperature sensitive. Their conductivity changes with heat. As temperature rises, more charge carriers become available, which increases conductivity. Second, semiconductors are dopable, meaning their electrical properties can be finely tuned by introducing specific impurities. This ability to manipulate conductivity makes semiconductors extremely versatile and forms the basis for designing advanced electronic components. These materials are critical because they enable digital control. By switching between conductive and non-conductive states, they facilitate on-off logic needed for binary operations in computing. They also offer precise control over electrical behavior, which is achieved through controlled doping. This is crucial for designing circuits with exact performance specifications. Semiconductors form the foundation of all electronics, supporting transistors, diodes, and integrated circuits. The impact is vast. In 2022, the semiconductor market reached $574 billion, with over 1 billion transistors packed into a single modern processor and 99% of all electronics containing semiconductors. What is diffusion? Diffusion is the process where atoms migrate from regions of high concentration to regions of low concentration. This atomic movement is driven by the natural tendency of atoms to reach equilibrium, an even distribution throughout the material. In semiconductor manufacturing, diffusion is used to introduce dopant atoms into the silicon lattice, enabling control over electrical properties in targeted regions of the wafer. Several driving forces govern this process. High temperature is essential, typically between 800 degrees Celsius and 1200 degrees Celsius. This heat provides the necessary energy for atoms to move through the solid material. Another key driver is the concentration gradient. Atoms move from areas where their concentration is high to areas where it is low. This movement continues until a uniform distribution is achieved. What is diffusion? Diffusion is a thermal process that redistributes atoms within a semiconductor wafer. The visual process shows how atoms begin in a region of high concentration. When heat is applied, these atoms start to migrate, spreading into areas of lower concentration until an even distribution is achieved. This atomic redistribution is key to modifying the electrical behavior of the silicon substrate in a controlled way. Why is diffusion essential? First, it enables the creation of p-n junctions, the foundational structures in all semiconductor devices. A p-n junction forms when p-type and n-type materials meet, allowing diodes and transistors to function. Second, diffusion allows engineers to control conductivity by adjusting the type and concentration of dopant atoms introduced into the wafer. This precise tuning is critical for device performance. Lastly, diffusion is what enables modern electronics to work, powering transistors, diodes, and integrated circuits that drive everything from smartphones to servers. Types of diffusion. Diffusion in semiconductor processing involves two main steps: predeposition and drive-in. Each plays a unique role in controlling how dopants are introduced and distributed within the silicon wafer. The predeposition step is the initial doping phase, where dopant atoms are introduced to the wafer surface. This forms a thin doped layer and typically takes 15 to 60 minutes. The dopants remain concentrated near the surface, resulting in a shallow depth of approximately 0.1 micrometers. This step defines the initial dopant profile and concentration. Following predeposition, the drive-in step redistributes those dopant atoms deeper into the wafer. This redistribution enhances junction depth and improves dopant uniformity. The drive-in process usually lasts between 2 to 8 hours and results in a much deeper penetration, typically 5 to 10 micrometers. Together, these steps ensure precise control over the dopant profile, critical for forming well-defined electrical characteristics in semiconductor devices. Types of diffusion. Diffusion in semiconductor manufacturing includes two major steps: predeposition and drive-in, each governed by specific time, temperature, and concentration parameters. Predeposition is the initial doping step that introduces dopant atoms onto the wafer surface. This process typically operates at around 950 degrees Celsius, using a high dopant concentration to create a thin doped surface layer. The duration is relatively short, ranging from 15 to 60 minutes, and the diffusion depth remains shallow, at approximately 0.1 micrometers. The goal here is to precisely place a large number of dopants near the surface. In contrast, the drive-in step redistributes those dopants deeper into the silicon. It runs at a higher temperature, around 1100 degrees Celsius, with a much lower dopant concentration, and for a significantly longer time, usually between 2 to 8 hours. This results in a deeper diffusion depth of around 5 to 10 micrometers, creating a gradual dopant profile optimized for forming junctions in semiconductor devices. Complete process flow. The diffusion process in semiconductor fabrication follows a structured sequence designed to precisely control dopant placement and concentration. It begins with the preparation of a clean wafer. Ensuring the wafer surface is free of contaminants is essential, as any particles or residues can affect dopant distribution and diffusion efficiency. Once clean, the wafer enters the predeposition phase. During this step, dopant atoms are introduced to the wafer's surface in a controlled environment. This creates a high concentration of dopants in a thin layer near the surface. Next is the drive-in step. Here, elevated temperatures facilitate the redistribution of dopant atoms deeper into the wafer. This step is critical for shaping the final dopant profile, allowing junctions to form at desired depths. The process concludes with a final profile that meets device specifications. The combination of predeposition and drive-in ensures both dopant placement precision and electrical performance reliability. The diffusion process steps. The diffusion process begins with wafer preparation. At this stage, silicon wafers are thoroughly cleaned and inspected to remove organic, ionic, and particulate contaminants. RCA cleaning, a standard method involving chemical solutions, is typically used to ensure surface purity. After cleaning, wafers undergo inspection to detect defects or contamination that could impact diffusion results. The second step is furnace loading. Here, wafers are carefully placed into the furnace tube under a controlled environment, usually at ambient room temperature, around 25 degrees Celsius. Proper handling is critical to avoid introducing particles or mechanical damage that can interfere with the process. Next comes preheating. This step ramps up the furnace temperature gradually to prepare the wafers for diffusion. Controlled and uniform heating, reaching approximately 600 degrees Celsius, is essential to avoid thermal shock and ensure even temperature distribution. This step transitions the wafers from room temperature to the thermal conditions required for effective dopant movement in subsequent diffusion steps. The diffusion process steps. The diffusion process advances with high-temperature doping, followed by stabilization. Step 4 is the active diffusion phase, where the wafers are exposed to a temperature of approximately 1000 degrees Celsius. At this stage, dopant atoms become highly mobile and begin diffusing into the silicon lattice. The elevated temperature facilitates deep and effective penetration, forming the dopant profile needed for electronic function. Step 5 is stabilization. After reaching peak temperatures, it's essential to maintain steady thermal conditions to ensure uniform diffusion across all wafers. The temperature is held constant at around 1000 degrees Celsius, allowing dopant atoms to distribute evenly and minimizing process variability. This stage enhances uniformity in junction depths and electrical characteristics. On the right, the temperature profile graph illustrates the heating and cooling curve. A gradual ramp-up in the first few hours, a plateau at high temperature during active diffusion and stabilization, followed by a controlled cool-down to prevent wafer stress or damage. The diffusion process. Steps. Following the high-temperature phase of diffusion, the cooling step is essential. Cooling is carried out in a controlled manner to gradually reduce the temperature of the wafers. Rapid cooling can induce thermal stress and damage, so a gradual drop from high temperatures like 1200 degrees Celsius to around 400 degrees Celsius is used to stabilize the dopant distribution and maintain wafer integrity. After reaching a safe temperature, the unloading step begins. Processed wafers are carefully removed from the furnace, ensuring they meet quality standards before moving to the next manufacturing step. This transition includes a quality check to verify uniformity and correct dopant profiles. In summary, the entire diffusion cycle spans 4 to 8 hours, reaching peak temperatures of 900 to 1200 degrees Celsius under a precisely regulated controlled gas environment. The process achieves plus or minus 1 degree Celsius precision and supports key benefits such as precise dopant control, uniform distribution, and efficient batch processing. Diffusion furnaces overview. Diffusion furnaces are critical tools in semiconductor manufacturing, specifically designed to introduce dopant atoms into silicon wafers with high precision. The primary function of the diffusion furnace system is to enable the controlled incorporation of these dopant atoms by heating the wafers to high temperatures in a regulated gas environment. A standard system includes heating elements, which raise the temperature within the quartz tube to levels between 600 degrees Celsius and 1200 degrees Celsius. Wafer boats, loaded with silicon wafers, are inserted into the tube and exposed to process gases that carry the dopant species. Gas flow is tightly controlled to ensure uniformity, and temperature zones are carefully managed to avoid gradient-related defects. Batch sizes can range from 25 to 200 wafers, allowing for efficient high-volume processing. The furnace maintains ideal process conditions through feedback-controlled gas flow, heating, and status monitoring systems integrated into the equipment. Diffusion furnace overview. Diffusion furnaces are defined by a set of key characteristics that enable precise and repeatable semiconductor processing. Temperature control with plus or minus 1 degree Celsius precision ensures that dopant atoms diffuse consistently across all wafers. Gas distribution is 99.9% uniform, which is critical for achieving reliable dopant concentration profiles. These systems are designed for 24/7 continuous operation, maximizing productivity. Multi-zone heating allows different sections of the furnace to be independently controlled, maintaining optimal thermal gradients. A controlled atmosphere ensures the exact composition and flow rate of process gases. The working principle includes 3 essential steps. First, high temperatures supply the energy needed for atomic diffusion. Second, dopant atoms are introduced via gas or solid sources. And third, these atoms migrate into the silicon crystal lattice. Overall, the benefits of diffusion furnaces include high precision, batch processing capabilities, excellent uniformity, and cost-effectiveness through high wafer throughput and repeatable performance. Furnace types and components. Diffusion furnaces come in 2 main configurations, horizontal and vertical, each with distinct advantages. Horizontal furnaces offer higher capacity, accommodating between 100 to 200 wafers, and deliver excellent uniformity. Their large footprint makes them more space-consuming, but they are relatively easy to maintain. In contrast, vertical furnaces handle smaller batches of 25 to 100 wafers, but offer a more compact design, making them suitable for clean rooms with space constraints. Vertical systems also provide better particle control, which is vital for yield enhancement in advanced nodes. Both furnace types rely on 4 critical components: heating elements with multi-zone control for thermal precision, gas systems to regulate mass flow and dopant delivery, advanced temperature control systems with plus or minus 1 degrees Celsius accuracy, and quartz process tubes that maintain chemical stability at high temperatures. Understanding these components and furnace types helps ensure optimal performance, throughput, and quality in semiconductor manufacturing operations. Furnace types and components, technical specs. Diffusion furnaces are designed to meet demanding technical specifications required for precision semiconductor processing. The operating temperature range spans from 600 degrees Celsius to 1200 degrees Celsius, allowing for flexibility in handling various doping profiles and materials. This range supports both lighter and heavier dopants and enables the fine-tuning of diffusion depths. Temperature accuracy is maintained within plus or minus 1 degree Celsius, ensuring that dopant migration is consistent and controllable across every wafer in the batch. Heating rates can be adjusted from as low as 1 degree Celsius per minute up to 20 degrees Celsius per minute, allowing either slow ramp-ups for thermal stability or fast ramps for time-sensitive processes. These furnaces are also built for continuous operation, 24 hours a day, 7 days a week, enabling high-volume manufacturing with minimal downtime. These specifications ensure that the diffusion furnace remains a robust and reliable tool, suitable for both R&D and full-scale production environments in semiconductor fabs. Applications and benefits. Semiconductor technologies are foundational to multiple key industries, each with unique demands and use cases. In the consumer electronics sector, semiconductors power devices like smartphones, tablets, and laptops. These technologies enable high-speed processing, compact form factors, and energy efficiency, core to modern digital lifestyles. Automotive applications include electronic control units, ECUs, sensors, and power electronics. These components are critical for vehicle performance, safety features, and the shift toward electric and autonomous vehicles. In aerospace, semiconductors play a vital role in avionics systems, satellites, and defense applications. These require high reliability and the ability to function in extreme environments. The computing sector depends on advanced CPUs, GPUs, and memory chips to deliver high-speed processing and data storage, supporting AI, gaming, and data center functions. Benefits include unmatched precision in manufacturing, accurate temperature control, high wafer capacity for increased output, and streamlined operation, all essential for scalable, high-quality semiconductor production. Applications and benefits. In semiconductor manufacturing, process benefits are central to achieving high performance, cost-effective, and scalable results. Precise doping ensures controlled addition of dopants, which is essential for defining the electrical properties of semiconductor devices. Batch processing allows multiple wafers to be processed simultaneously, significantly enhancing productivity and resource efficiency. High uniformity across wafers is critical to ensure consistent electrical performance, yield, and device reliability. Additionally, these methods are cost-effective, helping manufacturers reduce expenses while maintaining quality. The economic impact of these process advantages is profound. The global semiconductor market has surpassed $500 billion, reflecting its pivotal role in modern economies. Advanced manufacturing technologies have pushed yield rates up to 85%, meaning fewer defects and higher returns. Cost reductions of up to 30% are now achievable, and throughput has doubled, showing a 2x increase. Together, these benefits enable faster production cycles and more competitive pricing in a demanding global market. Applications and benefits. Semiconductor applications span a diverse range of sectors, with varying distribution across key industries. According to the application distribution chart, consumer electronics represents the largest share. This segment includes smartphones, tablets, wearables, and other connected devices that rely heavily on high-performance chips. Next, the computing sector is another significant contributor, encompassing processors, memory, and storage used in personal computers, data centers, and cloud infrastructure. Automotive applications are also expanding rapidly, driven by trends in electric vehicles, driver assist systems, and in-vehicle infotainment. Industrial applications include automation, robotics, and smart manufacturing, where rugged and reliable semiconductors ensure efficient operations. A smaller segment labeled Others may include areas like healthcare, telecom infrastructure, and smart home devices. The icons reinforce these categories, representing wireless communication, robotics and AI, power and energy systems, and computing and data applications. Together, this visual overview highlights how semiconductors enable functionality across every major sector of modern life. Conclusion and future trends. To summarize the key takeaways, semiconductor manufacturing continues to evolve around four major pillars. First, precise control, specifically atomic-level doping accuracy, is vital for modern semiconductor devices. The ability to manipulate material properties at such small scales enables the creation of highly efficient and compact circuits, essential for continued scaling and performance gains. Second, high throughput is achieved through batch processing efficiency. This enables multiple wafers to be processed simultaneously, dramatically increasing productivity and lowering per-unit costs. This is crucial in keeping up with the growing global demand for chips across industries. Third, the technology is highly versatile. It supports multiple applications, from consumer electronics to automotive, aerospace, and computing. Its flexibility allows rapid adaptation to new market needs and innovations. Finally, the economic impact is immense. Semiconductors drive a $500 billion-plus global market, acting as the backbone of technological advancement and digital transformation across the globe. Conclusion and future trends. The future roadmap of the semiconductor industry is charting bold advancements with major milestones ahead. From 2024 to 2025, the focus is on advanced node technology, including 3 nanometer and beyond, which enables even smaller, faster, and more power-efficient chips. By 2026-2027, quantum devices are expected to emerge more prominently, powering breakthroughs in quantum computing with capabilities far beyond classical systems. This will open doors to solving problems in cryptography, materials science, and AI. From 2028 to 2029, smart manufacturing will see deeper integration of artificial intelligence into production lines, driving efficiency, quality, and agility. Post-2030, green technologies will dominate as the industry shifts towards sustainable manufacturing practices, aiming for energy-efficient fabs and eco-friendly materials. The industry outlook reflects this progress. Expectations include strong annual growth, a multi-trillion-dollar market by 2030, millions of jobs created globally, and significant impact across dozens of countries, driving global innovation and economic development. Conclusion and future trends. Diffusion furnaces continue to be a foundational element in semiconductor manufacturing. Their importance lies in their role in enabling atomic-level precision, essential for processes such as doping, oxidation, and annealing. This level of control is what allows advanced semiconductor devices to function reliably and at high performance. As we move further into the digital era, diffusion furnaces help power the transformation driving every industry forward, from smartphones and electric vehicles to quantum computing and AI. These systems embody precision engineering, ensuring consistent quality and repeatability at scale. They are innovation drivers, evolving to meet the demands of emerging technologies and materials. And most importantly, they are future-ready, equipped to support the miniaturization, complexity, and sustainability needs of tomorrow's chips. Ultimately, diffusion furnaces do more than manufacture devices. They enable global progress. That's why they are powering tomorrow's technology today, at the heart of a smarter, more connected world.